This is the oscillator that I have been experimenting with in previous videos, nerds80, 83, 85, 86 and 87. And I still have problems with it. This time I will do experiments with the amplifier, entering a signal in here and looking at the output here with the interferometer. You can see about the interferometer how to use it in previous videos. So this is what I will be looking at. The latest video before this, I had an inductor here to get more output power, but that wasn't very good because then the voltage on the drains of these transistors became too high, so it got saturated. So now I have tuned it. These capacitors make the voltage very low here when I ground this point. That means I have series tuned the secondary. And then I found that I wanted this inductor and this resistor to get a resistive 50 ohm impedance at the output. I have set parameters for looking at very close range, so the baseband bandwidth is below 0.1 Hz. And measurements take a long time now. This has been running for 1 hour and 45 minutes. And I take notes about the readings I have at different offsets from 0.1 Hz up to 2 Hz. The output is 6.84 volts peak to peak into 50 ohms. The signal level into the interferometer is now 10 decibels lower. And the result is rather similar. I haven't read it out yet, but I can see it directly. The gain through the amplifier is 0.4 decibels larger. So there was 0.4 dB compression in the previous image. The numbers in the table is dBc per Hertz, but there is a 20 dB carrier suppression. So it goes from minus 100 at 0.1 Hertz down to minus 144 at 2 Hertz. With a 20 dB carrier suppression corrected for, I get these points. And they form a nice curve with the right slope in the beginning and bending a little bit here at minus 144 at 2 Hertz. So this is much better than what I can ever hope to get from the crystal. So it is sufficiently good. But there is a problem. I have been doing these measurements with the foam plastic on top of the box. Now, when I remove that, I don't change the electromagnetic situation inside the box. Well, the aluminium sheet, someone might expect it could have an influence, so I will put that back. Now the electromagnetic situation is the same, but acoustically, sound pressures of various kinds, they can enter the box now. The noise level is much higher, and we can see that easily in the waterfall. And I will wait for quite some time to get the proper sideband noise spectrum for the phase noise and compare with what I had with the foam plastic in place. I have made a new measurement at minus 10 dB. This time is significantly better. 3 up to 5 dB better at close range and not much different at 2 Hertz. So this looks frustrating. Could it be that this infrasound modulation is different depending on the power level, or is it something else? My friend Mart SM0ERR has been here, and he has the skills to work with surface mount component, so he has replaced the AD converter in this UADC4 prototype, and it's also modified. The front end is simplified greatly, just a capacitor into the differential amplifier for each channel. He also brought an infrasound microphone and a level meter to it. And as it turned out, there is strong infrasound in my little electronic workshop. And he told me this is perfectly normal. It's because of winds outside. The pressure varies a little bit inside the building. Right now, fairly late evening, the winds are very small, as you can see on this 3. It's not moving at all, which it always is doing nearly. Now, when there are no winds outside, and when the box is still open for infrasound, I have a problem with the leading at 0.1 Hertz. Signal to noise ratio isn't good enough, so I have to guess something maybe like that. That would be 82 or perhaps 84 dB. So I just skip that. Higher frequencies I can guess better and better. And this is now with the UADC4, and we will see that shouldn't make any difference at very close spacing, where the phase noise of the oscillator dominates, but it should make a difference at a little bit wider separations. I've put the lid back on, so now the box is well protected from electromagnetic fields as well as from sound waves, or rather air pressure variations. The main spectrum is not affected. The lid was on here, and it looks exactly the same. But in the narrow range, there is a significant difference, particularly at about this separation, and that is 0.4 Hertz. So I should see a significant change here at 0.4 Hertz, and I will wait until tomorrow before looking for that. The red dots down here is a measure of the noise floor of the correlated signal. It's the imaginary part, while the real part is positive and is the yellow trace. The separation between the noise and the upper uncorrelated, the blue channel 1, is about this much, and that is about 18 decibels, and that is for 679 averages. That is after 13 or 14 hours nearly. So I have a result here, and while the channel 1 is degrading, the noise floor approaches the signal, the yellow trace. So at this point, the yellow trace is not reliable at all. It shows -86, but it could be something else. So I will have to forget about the values I have had at 0.1 Hertz. I have to start at 0.2 Hertz, signal to noise ratio about 6 decibels. That's a not very precise result I can have, but it says -97. With the UADC4, it seems I can get a reliable result up to about 20 Hertz offset. Then comes the peak here, associated with the second harmonic on one side and the DC component, that means zero frequency, on the other side. So this region is useless, and here signal to noise ratio is very low. The noise floor improves as the x-axis is compressed, because averaging is done with complex numbers. So this is the separation I had before. And now the noise is down here somewhere. So I can read for 50 Hz that the sideband phase noise is about minus 152. These are the results I see now. The circles is with the lid on, and it is significantly more noisy than what I saw using the SDR IP in the previous video. But when the lid is off and the infrasound is allowed, I get the triangles here. And then the infrasound doesn't affect frequencies above about 0.7 Hz or so. And down at 50 Hz offset here, there is some degradation. Probably the measurement was uncertain. This is 2 decibels, so that is not a big problem. It seems I've made a mistake. The specification for the Wenzel oscillator says minus 140 at 10 Hz offset. So I should see it at about minus 160 with 20 decibels of carrier and oscillator noise suppression. So 160 at 10 Hz, that's down here. That's where I have this data point, about 1 decibel above what I saw in this measurement, where I had 50 decibels of carrier suppression. So probably what I see here is the Wenzel, mainly, because this is far below. And here is the Wenzel noise plus the infrasound noise. So I will repeat with a higher carrier attenuation. Now the carrier suppression is 40 decibels, and I have added amplifiers in the 2-channel receiver. And that lifts the noise floor of the receiver and increases the dynamic range of the system. I take down the numbers from this graph. When I compress the x-axis, I can read minus 140 at 50 Hz. But I can also see there is uncorrelated noise in channel 1 that is much stronger than in channel 2. So maybe I should look a little bit at the amplifiers I'm using. Here is what I got now with 40 dB carrier suppression. It's these points, and the line is a straight line, and about 2 decibels below the measurements I made with the SDR IP in a previous video. And that can be the precision by which I'm attenuating in the interferometer. I'm relying on the precision of an attenuator. This point must be wrong. Maybe it's because of the proximity to the spur from the zero frequency. I would need even more carrier suppression to look at this separation. Maybe it will be better further out, but then I need different parameters in Linrad. Now, the visibility of the infrasound, which was only 3 dB up here, should be much bigger, because it is of the similar level, roughly, as this signal here. So I should see it somewhere in this region. And I will have to look. I have swapped the cables into the sound card, And that changed the problems of excess noise at 50 Hz from channel 1 to channel 2. So that is something I could look at in the sound card. But right now I want to proceed looking for the infrasound. With the box open now, this noise is very strong and well visible all the way down to 0.1 Hz. I will plot these values on the paper. With the box open, I get these triangles, which is the infrasound modulating something in the box. The triangles are very close to the positions where they were before. I have used trimmer capacitors of these types. The blue is 120 pf and the other one is 10 pf. 10 pf is here and 120 pf here and here. I have tuned all the three capacitors for minimum capacitance to eliminate the risk that perhaps the thin materials here could be compressed or changed somehow when the air pressure varies. The balance in the interferometer is completely destroyed now. I have changed the phase, so I attenuate first by 20 decibels, 20 more, and then I have to change cable lengths to bring down this. Something like this, and now I fine-tune for this to be at the proper level. Already after half an hour I can see that the noise is a little lower now. It's about 3 decibels lower here, and then there is no difference. 1 dB and nothing. I cannot be sure that this is really because of the lowered capacitance. It could also be that the sound level of the infrasound changes a little from time to time. So I will isolate the problem. I will study the first amplifier only. So I cut here and I put a 50 ohm resistor to ground in parallel with the output. Means I have 25 ohms in this point. 15 ohms in series gives me 40 ohms here. And that's the appropriate load at this point. It should be 39, but 40 is close enough. Then I can see just this, and then maybe it will be easier. I have restored the tuning of this capacitor, approximately. And then I look at the sideband noise, and I find it is high. I have the numbers here. For the entire box, when it was with normal tuning and with a minimum capacitance. And this is somewhere in between. So the first stage is obviously pretty noisy. When there is infrasound at this. I have disconnected that capacitor completely. That doesn't improve the noise significantly. I write it down here. When I had it mistuned, it was like this, stage 1 only, and this doesn't differ significantly. Remember, the closed box was at these levels. That's about 20 dB below what I'm seeing here. So what else could be sensitive to air pressure? The noise of the first stage only, without the capacitor, is similar to the noise of the two amplifiers together when the capacitors were properly tuned. So the capacitors don't do much. The 6 transistors are mounted like this. They are glued to the bottom of the box. Now maybe these plastic things, epoxy with some silicone inside, they could be pressure sensitive. So I will rearrange how the transistors are mounted. The transistors are now surrounded by a copper wall. I will fill the space between the transistors and the copper wall and between themselves with this super glue, like this. I will then place this filler material on the liquid super glue. So the powder is now wet on the bottom but dry on top. I will put some more super glue on top of this. This gives me a very stiff material in a very short time. This may look nicer, but it hasn't changed the noise situation at all. The level without the lid on is the same as before, without the lid on. And just by putting the foam plastic on top of the box, I can see how the main peak here becomes much narrower. I have replaced the 18 pf polystyrene capacitor, actually 4 times 4.7 pf, with this kind of glass encapsulated ceramic capacitor. This should be completely insensitive to air pressure variations, while the plastic film inside this one could perhaps sense some outside pressure. And indeed, this makes a difference. Here is the original situation with the polystyrene up to this point. This short section is when I put the foam plastic in place. Here is with the ceramic capacitor and an open box. And here I put the plastic foam back. So I still have a pressure sensitivity, but it is smaller than before. With the box closed, I see the normal performance now when the box is rebuilt inside. With the box open, this is what I see. And I take down the numbers to plot on the paper. These crosses is what I see now. And this was the previous result. And so it's above here by 4 dB and below here by 2 dB. And I don't think this reflects things that I do to the box. It's probably more how the wind outside is changing. So the sensitivity is still pretty high for air pressure variations. There are not many components involved. This one was sensitive. It was the polystyrene. It is now a glass encapsulated ceramic. I don't think that could be sensitive. I have put these inside a stiff plastic, and this one is removed. And then there is the transformer, more or less solid iron powder thing. Maybe that can be compressed by the external pressure. That's not something that I can do anything about. I tried to replace this polypropylene by an old tube ceramic capacitor. That made no difference at all. And these are metal film resistors. I don't think they can be pressure sensitive. So it's just a mystery. Maybe it is the iron powder core after all. Anyway, I will have to keep the box closed to keep the pressure variations outside the range where I'm measuring the phase noise. I have added a high-quality capacitor, a trimmer, to tune the drains properly. This one is 10 pf maximum, like the previous one. This has made a significant difference, as you can see in the baseband waterfall, particularly at about 0.3 Hz offset. That's about here. It was white, and then goes into the green reddish range. So that is several decibels. It could be amplitude noise. I didn't look for that, but it could also be the phase noise. Or rather, it is more likely the phase noise, because that is what the winds mainly introduce. After 50 minutes, I can read levels within approximately 1 decibel. And that's accurate enough for now. The big difference here was probably due to amplitude noise, because the phase noise didn't change. Here I can see the amplitude noise is much weaker than the phase noise, and the development over time that the noise seems to be larger is probably a phase shift in the interferometer. So I will adjust the phase properly to see if something changes. There are occasional glitches. I have set a larger and slower waterfall to see if there is a pattern in the occurrence of them. I'm afraid they are caused by a mistake I made with the super glue. 2 thick layers of that and the powder on top of it may enclose liquid glue that will not harden until a very long time has passed. So if that hypothesis is true, I should see them occur at gradually lower frequency. It seems the glitches lift the curve from something like that to this. That is about 5 decibels. And they are not visible in the main waterfall, because the baseband started at 44 something, that's here. And this was probably something I did, I don't remember. I have cleared the noise spectrum after this event, and it has run for 18 averages now. And I see something like 93 decibels at 0.2 Hertz. That's normal for the closed box. And that's not what I saw when the glitches were included. So I will wait some time to see whether the frequency by which they occur will change, or if there is some other interesting pattern. It seems the super glue has stabilized during the night. These glitches, this was the last one. Here is when I retuned the balancing of the interferometer to see where the measurement started. And now it looks like this. At 200 Hz it's at -94. And it's nearly 1 hour, 53 minutes. I'm now injecting the signal here through 18 PF to this point to feed the transformer from a high impedance. And then I'm looking at the output here, and I don't remember what the output level is, but it's not as high as this. And there is nothing connected to this port. And this is to study the noise of this amplifier. This is what I see. The phase noise is very low. So, as usual, I take down the levels on paper to show in the diagram that I'm using. These are the points, the triangles, for the second stage, and it's about 8 decibels below the best measurements from the first stage, except for these 2 points but that is with a poor statistical significance. These levels are very low and not so easy to measure. I would have to use a larger carrier suppression, and then I run into stability problems with long measurement times. This very low noise level is of course with the box closed. With the box open, the noise levels are much higher. The infrasound related noise drops very rapidly as the frequency offset is increased. The second stage is obviously even more sensitive to infrasound than the first one. It is this curve I have found now, and it's about 30 decibels from here to here, even more. There are two polystyrene capacitors in here, this one and this one. I will just remove them and retune the phase and probably the amplitude also. Without those capacitors, the signal level is 3 decibels lower, but the noise is much lower. It was 68 here and then 73 that's about here. So the difference is in the order of 20 decibels. So I will try to find other capacitors. I have replaced the 68 PF polystyrene capacitor with this glass encapsulated ceramic capacitor and one old-fashioned trimmer of 40 PF, and I have tuned it to the proper position. The noise I see now is exactly the same as this curve, within 1 decibel. So the problem was not the capacitor, it was when I mistuned to lose 3 decibels of signal. And now with the trimmer I have increased the level by about 1 decibel. So maybe there is a small advantage, but nothing significant. It seems I have to accept the fact that amplifiers I build have to be placed in airtight boxes, because I cannot find a way to get rid of the sensitivity for infrasound. I mean air pressure variations at very low frequencies. So that's all for this video.